All right, let's get down to brass tacks and actually talk about hypotheses. So in the previous video, we outlined null hypothesis significance testing, and the first two words of that name is null hypothesis. So clearly this is something that's important, and we're going to define those here and think about some examples of hypotheses. So first of all, a hypothesis is a statement that is to be tested. So when we think of a hypothesis, we usually think educated guess, but really it just means some statement that is going to be tested. And there's two types that we consider for hypothesis testing. So there is typically what we use the original claim in. So we have the null hypothesis. Okay. The null hypothesis, which we typically denote H0 or H naught. So symbolically we write it this way, is the statement that we assume to be true unless evidence compels us to believe otherwise. So typically, whatever the original claim is for a parameter or a population's characteristics is what we end up using for the null hypothesis. We then also have the challenge, the alternative as in alternative music, alternative hypothesis, alternative meaning what else could be true, right? It is the challenge. You may sometimes see it denoted H sub A, but we're going to denote it H sub 1. This is standard in statistics. So this is the challenge to the null hypothesis. So the evidence that we gather tells us how to formulate this alternative hypothesis. But in general, this statement is the opposite, or it's included in the opposite statement to the null hypothesis. So the opposite or not included logically in the null hypothesis. So something that's really important, really important, the null and alternative hypotheses never overlap. So it's not possible for them to be true at the same time. Now, that doesn't mean, though, that H0 and H1 are direct opposites necessarily. Okay, so let's think of an example here. So here we have an example where we are assessing a claim by Boeing. Oh, that's a D, not a B. Boeing, which is a company that creates aircraft, claims that the rate of failure of their 737-8 MAX airplanes is the same as the rate of failure of their previous 737 models, which is about 1% of the time. So their claim is that, and we're going to use it as the null hypothesis. So the rate of failure, in other words, how often in a test batch there's a failure in the 8 MAX airplanes, okay, is 0.01. So 1 out of 100. The alternative hypothesis is given to us from alternative evidence. So given the notable incidents that involved the 737-8 MAX in 2018 and 2019, the FAA, which is the regulatory agency that oversees aircraft in the United States, claims that the rate of failure is actually higher. So the rate of failure is higher than, 0.01. Okay, so I've written these specifically in the form H0 colon statement, H1 colon statement. This is typical. We are going to use this format as we set up our hypotheses in hypothesis testing. Now, alternatively, we could have picked for the alternative hypothesis, the rate of failure is just not equal to 0.01, right? But we were given more precise information, and we want to use the more precise information. So symbolically, what exactly are we talking about? So rate of failure, by the way, is that among the population of these airplanes, the 8 MAX airplanes, how many of them fail or have failures, right? Number of failures. You might recognize this then as a proportion. This is a proportion. So what we're examining then is a claim about a population proportion. And symbolically, we might write this as, if we denote this population proportion as P, we're saying that the null hypothesis is that this proportion is exactly equal to 0.01, and the alternative hypothesis is that this is greater than 0.01. Okay, so this is how we would express our hypotheses symbolically. And notice that there is always going to be a null hypothesis and one alternative hypothesis. No overlap. It's not possible for P to be greater than 0.01 and equal to 0.01 at the same time. And if we chose to make this slightly different and wanted to go for exactly opposite statements, then we would say the alternative hypothesis is that the proportion is not equal to 0.01. So the rate of failure is just not equal to 0.01. So that's one example. Let's see another example. Having to do now with in case we have two samples, two data sets, right? So you may have heard of a phenomenon referred to as the gender wage gap. So this is a phenomenon that refers to the difference in salaries and hourly earnings between male and female participants in the workforce. So if you could think of the population of males and females in the workforce, men and women, and in these two populations, two different people selected at random in the same industry at the same title level earn possibly different hourly wages or salaries. And so it turns out historically and contemporaneously, so even today, if we count for all of the variables such as industry level experience, geographic location, men in the aggregate, on average, consistently out-earn women. So the basic claims and counterclaims of this academic debate are essentially about the equality of means. So namely, if we choose to denote mu sub m is the population mean of men's earnings, maybe hourly, so hourly, and mu w is the same parameter, the population mean, but for women's earnings, again, hourly. Then the null hypothesis may be stated as the means are equal. So mu sub m equals mu sub w. And the alternative hypothesis is that the mean for men is greater than the mean for women. So this gives us a statement about, so claim about equality of means. And to better understand how to analyze such statements, we may be interested in, I'm going to represent them as mu1 and mu2 now. The actual labelings, they don't matter, right? So 1 and 2, whoever is 1 and whoever is 2, doesn't matter as long as we're consistent. But we can write the same statement as, so equivalently, their difference, so mu1 minus mu2, is equal to 0. So the difference between the means is 0. And so a similar inequality statement, so the mean for men is greater than the mean for women, can be arranged in terms of the same difference. And then we're saying the difference is positive or negative, right? So now we've restated the claim in terms of difference of means. So equality of means is the same as saying the difference of means equals 0. And in these two examples, what we've covered already is we have what it would be called a one parameter test, or one parameter set of hypotheses. And here we have two parameters relating to two populations, and then we would need two samples for the second example as well.